and summer season to investigate the seasonal variation. We used the GIS and GPS tools. In addition to that, we conducted field analysis regarding pH, EC, dissolved oxygen, temperature. The analytical techniques used at the lab to measure MTBE and BTEX compounds were purge and trap concentrator, gas chromatograph, mass spectrometer, in addition to another system, purge and trap concentrator, but now gas chromatograph fitted with a flame ionization detector. Here, the results of field parameters. You can see here that in Amman Zarqa Basin, the pH was normal and within the acceptable range from 6.8 to 7.7. Regarding dissolved oxygen, we have a large variation in dissolved oxygen in the wells, as you show in the drawing. And for turbidity also, we have here also variation in turbidity, and we have extreme value up to 43.5 NTU, and this is due to pumping rate higher than capacity of aquifer. In addition to that, you can observe here the electrical conductivity values, that it is varied from low to high, and the high values for some wells are related to over abstraction of from these wells. Temperature, it is normal and within the normal range from 17 to 27. Regarding the other study area in Northern Governorate Yarmouk Basin, also the pH is normal, dissolved oxygen also, in addition to turbidity. Regarding electrical conductivity also, we still have extreme values for EC for some wells as shown in the drawing. The temperature also, we still have extreme value for North Shuna well. It is considered thermal well. Now, according to the main study regarding the detection of MTBE and BTEX, we detected some MTBE in Hashimiyya well, number 2 and 5, but this was done only for one time in summer season. And this sign of contamination was disappeared again in winter season, and the results was below the lowest reportable value, which is below 1 microgram per liter. And how we explain it? We explain it that it might be an accidental release from oil tanker or the result of deliberate leak into water wells through the fractures and unconsolidated aquifer B2A7. The significant decrease in winter season also is due to the rainfall and dilution of the contamination and the flushing of the polluted pulse. Yani, what I would like to explain that it is not point source contamination. It is non-point source of contamination, and it has happened once, and it is gone, maybe by rainfall or other reason. Regarding, this is for B2A7, in this case, upper aquifer is safe regarding the concentration or the release of MTBE from gas tanks into aquifer. Also, the middle and lower aquifer, the middle aquifer also showed low levels, and it is not detectable and below the LRV, and also it is characterized, this aquifer, as a protective layers from the above formations, which is high clay content acting as a previous layers. The depth of the groundwater is more than 100 meters, which means a very long pathways to pass through into the aquifer. Regarding the lower aquifer also, the level was below 1 microgram per liter, and it complies with national and international guidelines for BTEX. In this aquifer, lower aquifer, the depth of wells is very high. Overall results, we concluded that the MTBE have revealed that concentrations of most monitored wells in Amman Zarqa Basin and Northern Governorate were not detectable and below LRV and comply with national and international standards. In theory, these results should be positively correlate with the rainfall rate and negatively with the sampling depth well, which means deep wells should be less subjected to contamination than shallow wells. The transfer of these compounds takes longer time to reach aquifers, although the movement of MTBE into aquifer is very high and exceeded BTEX compounds. Conclusion, the study covered water resources vulnerability due to MTBE and BTX pollution in Amman Zarqa Basin and Northern Governorate. The investigation considered the variation levels on the long term, the depth of wells, and the type of aquifers. This study is a first step in establishing a monitoring program for these substances in Jordan. And the study covered actually 131 groundwater resources, which included 258 water samples during winter and summer seasons. And the results, as I mentioned earlier, were below the LRV. There is no contamination. This is good results. No results is good results. And still our water resources in that monitored area is safe. But what we recommend to continue monitoring those compounds in water resources and monitor their levels in soil sample undertaken the fuel tanks in certain critical sites. In addition to develop the specifications of gas stations to maintain the integrity of the sustainability or of the quality of those of these sources and to prevent arrival of any pollutants in the future. As I mentioned earlier, this project was financed by scientific research funds and it lasted for 2 years. The researchers shared in this project, all of them are from Water Authority of Jordan, me, by my colleague Refaat, Bani-khalaf, chemistry Yahya Saleh, engineer Maher Harishat, and Saleh Abu Lheja, in addition to the professor Dr. Mustafa Al-Qaisi from University of Jordan. We would like to acknowledge Scientific Research Fund for their financial support and also Water Authority of Jordan for their facilitation to adopt this research and use sophisticated instruments to measure these compounds. And thank you for your attention.
Thank you very much, Ms. Randa. That was very interesting to see the very methodical activity. I was wondering at some point in time, would service station be included? And there comes the slide which shows that service station were also included, not just the gas station. This is very good. And we'll talk more in the discussion session. I would like now to welcome our fourth speaker for today, Mr. Olivier Depraz. Mr. Olivier has a business degree from the Bordeaux University for Business, Bordeaux Business School in 1988, and he holds an MBA from London Business School since 1995. He has 20 years experience in sales advisor for marketing advisor for several international companies. I believe working in the area of advanced technologies in management of natural resources. I would like to welcome Mr. Olivier, who is also a founding partner and CEO of ImaGeau. Did I pronounce it correct? Okay, thank you.
Here we are. Good morning, everybody. So, my name is Olivier Depraz. I am the General Manager of ImaGeau. I will start my presentation with a brief presentation of ImaGeau. Then I will talk about new technology, and I will present you the GMD, a new subsurface monitoring tool that we have invented. And at the end, I will share with you the outcome of the study we have carried out with Aegis on AZRAQ Bassin. First of all, about ImaGeau. At ImaGeau, we are specialized in well field management for depleted aquifer. We are 9 persons are used to work for ImaGeau. They are mainly engineers, hydrogeologists, or geophysicians. Our objective is to find solutions for sustainable water exploitation. So we are implementing network monitoring. We collect the data, display the data, then we are doing analysis, and we deliver expertise to find the best solution for sustainable water exploitation. We have 30 references worldwide, mainly in France, but in Jordan too, in Israel or in Chile, with big company, with ministry, and sometimes with water body. Now let's talk about innovation. The GMD is a monitoring device that we have invented at ImaGeau to know exactly what happens in the underground water resource. The innovation consists in situ, automatic, and repeated measurement of electrical resistivity. As you can see here, we inject power into 2 electrodes, and then we get back the power back, and we measure the power back. So we have the measurement of electrical resistivity in the whole aquifer. So you have this kind of graphic where you can see 4 profiles in a coastal aquifer in Charente-Maritime in France. Well, this is resistivity, but in hydrogeology we need conductivity. So thanks to a very famous and very well-known equation, which is here, over there, the equation of Waxman and Smith, we can go from the resistivity measured by the system to the conductivity. The conductivity is the result. What we need is in blue, and what we have in orange is 2 parameters that we have obtained thanks to logging. So now we have the conductivity, and we can see the same graphic in conductivity. And what you see here between 11 meters and 14 meters is the saltwater intrusion effect on an aquifer. And if you are doing this kind of profile many times a month and year, you can have this kind of graphic here, which represents in 3 days the effect on the brackish water and the fresh water. So in abscissa, you have the time, and in color, you have the evolution of the water quality. So here, what you can see is that between 11 and 14 meters, especially in summer, you have brackish water intrusion. But at the end of summer, when the recharge is on, then you go back to the fresh water. So what we can deliver as an expertise and the analysis of this kind of graphic will explain that the aquifer is going back to its normal state. So this aquifer is not overexploited. Of course, this tool, the tool we have developed, is completely different. That's what you know. Because, as you can see here, this is you have many electrodes all along a cable. And you can adjust the download spread, you can adjust the density of the electrode, and you can adjust the frequency of the time period from hours or minutes to weekly period. It depends on the phenomenon that you want to observe. okay, you can go to the depth of 300 meters, sorry. I don't know why it's going like this. And then you can put your electrode just on the saltwater intrusion that you want to do. And what you have is a precise display of in-situ process and the dynamics, about the dynamics. Here is some pictures of our tool. You can see the data acquisition box, because you don't need to go on field. All the data are sent to a server, and the data are displayed on the web application. So from your desk, you can see exactly what happens. And of course, we have developed a web-based interface, which is a very friendly user interface that everybody can use. So you get online access to all data. You have a graphic interface. You can download all the data from the well field, even other sensor, not only our sensor. So from your desk, you can see exactly what happens in the well field. And of course, our system is remote control. So from your desk, you can change the frequency. You can do a lot of things. Now, let's talk about the outcome of the study. We carried out the study with Aegis. I don't know, it's running without me. Okay, we carried this study with Aegis, with a French company, a French engineer company, which is here in the room. And the idea was to understand exactly what happens in order to deliver a solution to extend AZRAQ lifespan. First, we have to understand the saltwater movement. Then we have to discriminate the geological layer contribution to the salinization process, and at least validate two different salinization assumptions given by previous study. We run this study in 3 phases. First phase, preliminary study. Then we have to put and install the monitoring network with our local partner, Nabil Wakili Corporation Company. And then at the end, make the data interpretation to deliver a conclusion. The study was funded and financed by the AFD under the management of the Ministry of Water and Irrigation. The context, I think now you know the context of AZRAQ well field. This is a strategic water resource for Jordan. It is overexploited, and this salinization process could compromise water exploitation at least. So we have installed 3 monitoring systems in the red circle. Here you can see some picture of the installation and the steel boxes built by Nabil Wakili company. We drill and we install the system inside the hole. So results. First result coming from AZRAQ 2. What we can see is from 150 to 170 in the B4 layer, water conductivity is increasing continuously at all depths. And during the study, a 20% increase has been observed. Another result coming from AZRAQ 3, coming from the GMD. Here you can see that the salinity flow is measured by AZRAQ 3 during the recharge period. This salinity flow only affects the shallow layer, but the water conductivity is stable into the B5 aquifer layer. You can see the difference between red and blue here. So in September 2016, what we have understood is that the overall conductivity is increasing and was 1,577. And if nothing is done, we assume that the conductivity will be in 2000